And next and final talk for the session, Aleksander Wennersteen from Pascal.
Yeah, thanks. Yeah, I'm Aleksander. I'm here to present our work on Qadence, which is, I say, a domain-specific language for quantum computing, especially for what we call this digital analog paradigm. And this is a sort of high-level talk in terms of the language, and you might be interested to know that this is now also the main framework for quantum computing that we use at Pascal. So there's been a lot of, let's say, user-friendly choices taken as well. Quick overview is that we'll basically first just cover the definition of what we mean by digital analog, especially the analog part. I think it's quite probably unfamiliar to much of the audience, and then we'll effectively walk through the different parts of Qadence. So to begin with, to be sure that you know everyone's able to follow, we view quantum from the point of view of physics. So we think of a quantum state that evolves through time. So a quantum system in that sense then is described by the Hamiltonian, which is basically the energy of the system, and the sort of evolution through time is then expressed by the Hamiltonian operator, and that's what we say that we are programming. If you were here throughout the week, on Thursday there was a talk on semi-q, which is kind of following a similar idea, even calling it Hamiltonian oriented. So to begin with the distinction between digital and analog quantum computing, we say that in digital we think of discrete actions, whereas in analog we're thinking that we're programming this Hamiltonian continuously in time, and that by an analog device we mean something which has a native execution of the time evolution of the Hamiltonian. And this is quite possibly trying to do something of practical importance with quantum computing, quite possibly superior in the short term at least, and so the idea is basically with digital analog quantum computing that will try to take the best of both worlds. We'll work with, let's say, single qubit gates from in the digital sense, and we combine this with analog entangling operations. And some people have shown that you can think about quantum computing in this way, and it still turns out to be universal. Right, so we're a hardware manufacturer. That means that we obviously have what we build in sort of most important object. So our device follows this Hamiltonian here. The exact mathematics is not very important, but basically we end up having this programmable laser pulse which acts on all qubits, and that we have a programmable register, at least like a reconfigurable register which only acts between neighboring atoms. This Hamiltonian has the shape of a Ising Hamiltonian, which is something which physicists get very excited about because they spend many years studying this model, and there has quite a lot of applications also, modeling systems in this manner. In particular, graph problems that you can, we say, natively embed into this Hamiltonian. So that's the kind of applications that primarily targeting. So why do we choose to build a new quantum framework? Don't we have enough? Well, in the digital sense, yes, both high level and low level. In the analog, there's less, and most of them are really targeted towards programming a specific device. It really requires that you understand the physics of the device very well. We'll see an example later. Alternatively, now we have this sort of high-level semi-q approach. Unfortunately, it's very quickly that you end up with a laser pulse which we cannot currently execute, and be true to the program that's written. As such, we've introduced Qadence, and it's differentiable, so we work mostly with variational quantum algorithms. So you have some parameters, you execute a program, and then you want to run a loop where you calculate the derivative of your parameters, and you want to update them. We work in the quantum circuit model, and we say that a circuit is composed of blocks that corresponds to operations. Now, in the first bit, what we'll mostly talk about is this type of block here. This is the time evolution operators. This is an analog block, and we'll talk about the rest later. So, in some sense, this is the key idea of Qadence. It's that we try to remove ourselves from this really hardware physics point of view of programming the laser pulses, and we try to abstract that for our developers and think in a more quantum information theoretic manner that they're more accustomed to. As such, well, first and foremost, we have some concept of dimensionless units that we can then compile into what the hardware wants to do. This is work in progress. In particular, time is still a real unit. We'll talk about the syntax later, but we compose operations through time, and we separate out the different terms with the Hamiltonians. In this case, we can rotate in the x direction all qubits, and then we can have this analog interaction where you kind of entangle the system according to the register, which is again going back to before, is how we can maybe solve graph problems in the analog model. So compare this to Pulsar, our other library. This is really how it looks like when you're programming current analog devices. You end up having lots of numbers floating around which are really tuned to the values that the device takes, and you have to understand, again, the physics of the device, and you end up having, this is the program being realized, and you have to experiment your way towards finding the correct time to do things. This is not very important, but again, compared to this approach here, it's we're hoping to develop something which is slightly higher level. So onto the key parts of Qadence. We, working from the top down, on the outer layer we have this quantum model. It's effectively thought of as an abstraction of the backend. So a backend can be a QPU or a numerical simulator. And as a sort of key point of view, we think of this as encompassing a whole hybrid quantum classical program, again, variational algorithms. And for convenience, we've built this on top of PyTorch, the machine learning library. So we'll see later, we can have differentiable programs, and it's very user-friendly, to at least our developers, and it really represents the compiled executable program that can be done on the device. And in this case here, we've assumed the existence of a circuit. We've just made an observable. You often end up evaluating the state against an observable in variational algorithms. Right. So, and the model has functions like calculate expectation values, sample, run. We also have domain-specific quantum models for specific algorithms, or also to provide convenience functions like tomography, say, right, to recreate the state from bit strings. The next level of abstraction will be quantum circuits, taking the fairly normal definition of a quantum circuit. It really encapsulates the quantum computation part of the program, and we've decided that, for us, quantum circuit is really a final step. We're decided that once you made a quantum circuit, you're supposed to not do anything more with it outside of having it run, in the program through the quantum model. All right, so how do you make a quantum circuit in Qadence? You need a register. Again, for our device, it's quite useful to be able to just have a graph with positions and put them in. As such, we've developed these abstractions. But we can perhaps talk more about the blocks. So we say that quantum operations are blocks. They can be parameterized. We have like a distinction between primitive blocks and composite blocks, where primitive blocks represents, if not hardware executable, then these, kind of a real quantum computation. And we were inspired by, sort of functional programming approach when you compose the program. So we say we chain them through time, or we cron them in parallel. When you're doing with analog quantum computing, you can't rely on the compiler to figure this out for you, unless you really have a super high-level language. And you can add blocks, because you also use blocks to create Hamiltonians. So we see this here on the picture as well, that we have, in this case, digital gates. We can have analog operations. We can have these sort of digital analog operations, and we can combine them, and they're all, a block. And the blocks are, relying on being executed according to the register. So we think we might have some cool possibilities to do there by combining those on your program. And yeah, symbolic parameters. This is a very key abstraction for us in practice for our developers. So let's see. So one of the blocks is a Hamiltonian block. So here it's basically, this instance is this Hamiltonian-oriented programming approach, where you can, define a Hamiltonian. This is just a sort of initialization function. You can supply a register. You can supply a custom Hamiltonian that you write using the block system. We also, of course, apply sort of standard Hamiltonian, like the one that we can execute on the device, which you can then modify with the, interaction strengths manually. And this is, I think, one of the key challenges if you want to really write a digital analog quantum program and do something which you can't do with a different abstraction, is going to be that we'll have to be able to write, any arbitrary Hamiltonian like this and manage to compile it or do this, what we call a digital analog transformation into the system Hamiltonian. So this is a quantum machine learning circuit. This is sort of our main in practice type of program. So here you see a little bit how you could create a very basic program. You compose in parallel, so acting on all qubits, digital gates, because then you can encode the data in each qubit and have, sort of different parameters in each qubit. Otherwise, you're really losing a lot of expressibility. You can then create a register based on the problem topology, again, to leverage this analog evolution. And we can have, this variational ansatz, which is typical in variational algorithms like VQE or quantum machine learning, where you can supply the analog operations, which, of course, you can specify, which qubits this will act on. So you end up having a bit of flexibility in experimentation. And then, you compose that in the circuit. And this here is really what we hope is executable in the near term on our devices, which could be exciting. As you might have seen, neutral atoms devices are growing in size quite rapidly with a lot of restrictions. This works like a quantum model, works as a PyTorch model, as I said before, so you can put this into a optimization loop based on PyTorch, and it all works nice. It's natively differentiable, which means we just overload the PyTorch automatic differentiation engine. So some of those methods you can use on hardware. Of course, that means that you execute many circuit evaluations, because by this what we mean is you want to have a parameterized quantum circuit, you want to calculate the derivative of one of those parameters, so you end up having to execute a parameter number of circuit executions times your shot count. And we have implemented this more general parameter shift rule, which will allow us to not just take derivatives of simple operations like the digital gates, but also more complex digital analog operations. So I'm going to skip ahead to this slide here, since we have time. So as I said, this digital analog approach it can turn out to be universal in some limits. So this is actually a quantum Fourier transform. I'm not going to be able to cover it in much detail, but this is how you imagine that a more complicated circuit would look like, and it shows some of the key ideas of the paradigms where you have, we talk about generators, so like an sort of a Pauli operator generates parameterized Hamiltonian operation. So instead of having C-phase gates, you would end up having this analog interaction, which you'll have to compile using this digital analog transformation ideas. And yeah, this is just quick. Just skipping back to the summary. Focuses on building programs which are executable today or in the very short term for our developers to use, day in, day out. For analog, digital analog, and digital analog modes, and that it's sort of trying to move away from thinking about physics, I guess, really working in the opposite direction of what most people here work in. Higher level interface, really borrowed from this GU library João and Kuiper, the idea of blocks and composable circuits. I think this is a great way to, in the near term, build a larger program, and it's all differentiable. Future work, we'll be working on trying to open source more of our internal libraries built on top of Qadence, so that will further enrich the syntax according to problems. Compilation, one thing which will be very interesting is that the register on Rydberg atom devices is reconfigurable during execution. So you can imagine composing blocks with different registers, and the compiler will have to realize we will have to, move the atoms physically in the device between stages, and also work on these transformations. Thank you very much.
Okay, thanks, Aleksander. I'm having the first question. This system, if I understood right, you can do a register of any graph, and you can have any interaction on the edges. So it seems like a great system for doing measurement-based quantum computing. Have you looked at that?
Not personally. I know we have people that have worked in this direction. We've not really said anything about it publicly, so I think I'll have to leave it at that. I have some colleagues in the back. I don't know if they know anything we can say.
We can't do measurement-based.
Yeah. Very, very early stage research.
Any other questions? Oh, sorry.
Yeah, I have a kind of a vague question about what's you kind of foresee people interacting with this. So the point is to kind of get the physics knowledge kind of out of this, so you have developers interacting with this system. Do you think there's a right level of abstraction that a developer who doesn't understand the physics can really understand well enough what this analog step is doing in the computation that they can use it in an effective way?
Yeah, I mean, this is really the key idea that we're thinking about with this analog rotations is that, well, okay, maybe, for analog you really will require physics knowledge, but at least maybe you can have, a general introduction to quantum mechanics course and not, a full master's in optical, like sort of manipulating atoms with optics. Mm-hmm. And yeah, in terms of, that's also the point of the block system, right, is that we think maybe you can more easily write programs for, an academic group in Germany in spring managed to have 10,000 atoms trapped in a single device. So we're potentially looking at that level of atoms in a very short term. 5 years ago, no one was doing neutral atoms. So we're really just trying to scale the computation model step by step. We'll see.
So how specific is this to your hardware, and are the ideas here applicable to both other like neutral atom systems and to the ion trap and superconducting qubit devices?
Right. Yeah, I think I had planned a sentence that I skipped. It's definitely applicable to other neutral atom systems, especially the ones which have an analog mode. Mm-hmm. So that's occur at least. Yeah, I mean, we can definitely write the sort of compilation step of translating this either via trotterization to a fully gate-based basis, or if we can get the pulse level access, say through superconducting hardware, then you will have the possibility to realize Hamiltonian. Just so happens that neutral atoms have at least these Hamiltonian, so it's kind of into like easy to start going. Whereas I foresee other hardwares at the pulse level, which is where we're currently mostly working, is significantly harder. But if we have time, we'll definitely explore it.
I see. Yeah, as I understand it, there's nothing is natively using gates. It's just a question of whether or not they're exposing their pulse interfaces.
Yeah, exactly.
Thank you.
Last question? No takers? Okay, thanks very much, Aleksander.
Thanks.